Section 5.1, Modeling Data with the Quadratic Function. A quadratic function is a function that can be written in standard form such that f of x or y equals ax squared plus bx plus c. A is the coefficient for our quadratic term because it has an x squared. B is the coefficient for our linear term because the x has an exponent of 1. And c is our constant, where a cannot equal 0. If a equals 0, then our quadratic term would drop out, and it wouldn't be quadratic, it would be a linear function, which we've already discussed in previous chapters. Its graph is a shape of a parabola. A parabola looks like a U. It can either go up or it can go down, and that is dependent on the coefficient of our leading term for our quadratic term. Standard form of a quadratic function is f of x or y equals ax squared, which we already stated is the quadratic term, bx, which is the linear term, and c is the constant. Quadratic functions have graphs that are parabolas. A parabola is the set of all points whose distance to a fixed point, called the focus, and a fixed line, called the directrix, are the same distance. Here we have a diagram. We have a parabola, a directrix, and a focus. We have a point on the parabola, and if we draw a segment to the focus and the directrix, of course a constraint that it's perpendicular to the directrix, we have segments that are congruent. As the point travels along the parabola, we are going to have segments that are still congruent. As the distance grows from the directrix and the focus, we still get congruent segments. And that is true for every point on the parabola. That's how we get the definition of a parabola. This section will not go much deeper on the focus or the directrix, but we will identify other definitions of a parabola. Here we have the axis of symmetry. The axis of symmetry is a line that divides a figure into two parts that are mirror images. Here, our axis of symmetry is in blue. Notice every point on the left is mirrored or reflected over the axis of symmetry the same number of units away. 1 unit here and 1 unit here. That occurs all the way on each side of the parabola. Notice in green we have a y-intercept. We already know that that's where a point intersects the y-axis. Notice also that it's reflected over the axis of symmetry and it's the same number of units away. And that's what's identified on the other side. The y-intercept is reflected over the axis of symmetry. Here, a point that lies on the parabola and on the axis of symmetry is called the vertex. The vertex will have either a minimum value, such as here, this is the lowest y value in our parabola, or if the parabola was inverted, pointing downward, that vertex would have the maximum value in the parabola. The vertex is the point where the function for the parabola reaches the maximum or minimum value. The parabola intersects its axis of symmetry at the vertex. And here it's identified where my parabola is pointing up. I have a vertex that is a minimum value, the lowest y value in our parabola. Here I've identified a parabola that opens downward, and I have a vertex, but this vertex is the maximum value or the largest y value in my parabola. The first example asks us to determine whether each function is linear or quadratic. Recall, a linear function has a variable with an exponent of 1 and a possible constant attached to it. A quadratic function has a variable with an exponent of 2 with a possible linear term or a constant term attached to that. Once we identify what we have, we want to identify the quadratic, linear, and constant terms. Number 1, we have f of x equals 3x minus 5, or y equals 3x minus 5. Here our variable term has an exponent of 1. Therefore, I know that this is a linear function. And that is our linear term. 5 is our constant term. Number 2, y equals 4x squared minus 3x minus 5. We have a variable term that has an exponent of a 2. Therefore, this is a quadratic function, and this is our quadratic term. The negative 3x is another variable term. It has an exponent of 1, and that represents our linear term. And minus 5 is our constant term. Example 3. F of x or y equals a negative 2x squared plus 5. Here I have a variable term with an exponent of 2. Therefore, this is a quadratic function, and this is my quadratic term. I have no linear term because I don't have a variable term with an exponent of 1, but 5 represents my constant. Our last example, f of x equals a negative x times quantity of 2x minus 6 minus the quantity of 3x minus 4x squared. We need to simplify by distributive property and combining like terms first. That gives me a negative 2x squared plus 6x minus 3x plus 4x squared. Combining like terms, negative 2x squared plus 4x squared is 2x squared. 6x minus 3x will give us 3x. Therefore, I have a variable term with an exponent of 2. Therefore, this is a quadratic function, and that is my quadratic term. And this is my variable term with an exponent of 1. Therefore, that is my linear term, and I have no constant term. On this slide, they want us to identify the vertex and the axis of symmetry for each parabola. On my first parabola, I'm given a parabola that opens down. My vertex is at the maximum point, and that is located at a negative 1, 1, 2, 3, 4, 5, 6. So my vertex is a negative 1, 6. The axis of symmetry must be a vertical line in these parabolas that we're using, and it must also have the vertex that is on that line. Therefore, my vertical line would be the vertical line intersecting the point negative 1, 6. And recall that a vertical line intersects only here the x-axis. Therefore, that function is written as x equals, and I use the same variable that is in my ordered pair, negative 1. So here is the equation for my axis of symmetry, and here is my vertex. On the next parabola, I have a vertex that is the maximum point that is located at 0, 1. And the axis of symmetry also intersects that vertex with a vertical line, and that vertical line runs through the x ordered pair. And recall again, the vertical line has to have only the x variable, which is x equals 0. On this slide, again, they want us to identify the vertex and the axis of symmetry for each parabola. Here, I'm given a vertex that is a minimum point in our parabola. It is located at a negative 1, 1, 2, 3, 4, negative 4. And its axis of symmetry must intersect that point at a vertical line. And its equation is the intersection of the x-axis, x equals, here, a negative 1. The next example, I have a parabola with a minimum point for the vertex. Here, that is located at 1, 2, 0. The value for the vertex or ordered pair. I have a vertical line that intersects that ordered pair for the axis of symmetry. It is located with the equation of x equals 2. Our next example. For each parabola, identify the points corresponding to the points P and Q. In other words, they want the points that are reflected over the axis of symmetry. Remember, it's the same distance away on the axis of symmetry for each point. So here, I have my vertex, and I know my axis of symmetry is the vertical line that intersects that vertex. This vertex is a minimum. And for my point P, it is 1, 2, 3 units away from the axis of symmetry. So the corresponding reflected value for P would be 3 units to the right of my axis, 1, 2, 3. And I'll call that P sub 1. So P sub 1 has an ordered pair that is 1, 2, 1, 2, 3, 4, 5. Q is 1 unit to the right of my axis of symmetry, so its reflected point over the axis would be 1 unit to the left. And I'll call that Q sub 1. That is located at a negative 2, 1, 2, 3, negative 3. Our next example, again, I can have an axis of symmetry that intersects my vertex. Recall the points are equidistant or the same units away from the axis of symmetry. Here I have Q. Q is 1, 2, 3 units away. So Q sub 1 would be located 3 units away. And its ordered pair would be 1, 2, 3, 4, 5, up 1, 2, 3, 4, 5, 6, 7, 8, 9. Q sub 1, 5, 9. P is 1 unit to the right, so P would be located 1 unit to the left, or P sub 1, 1 unit to the left. And that would be located at 1, 1. On this example, we are asked to find the quadratic function to model the values in the table. Remember that our model for a quadratic function is y equals a x squared plus bx plus c. And with this table, we know the values of x and y for each ordered pair. So let's generate 3 equations with these ordered pairs. So in other words, negative 1, 4, I want to create a function with this in mind. So in place of y, I'm going to plug in a 4. In place of x, I'm going to plug in a negative 1. A negative 1 squared is 1a. In place of x, I'm going to put in a negative 1. A negative 1 times b is a negative b, plus c. So now I have an equation of just a, b's, and c's. Let's do the same thing with the second ordered pair. Here, in place of y, I'm going to put in a 1, so that's 1, equals. In place of x, I'm going to put in a 0. 0 squared is 0. 0 times a is 0. So I have no value of my quadratic term. For the next one, I'm going to substitute in a 0 for x. 0 times b is 0, so therefore that term drops out, and I'm left with c equals 1. For my last ordered pair, I'm going to substitute my 0 in for y and get 0. For x, I'm going to substitute in a 1. 1 squared, 1 times 1 is 1, times a is just a. Substitute 1 in to x, 1 times b is b. And I have a c. Now I'm given 3 equations with unknowns that I need to solve for. And here I already know that c is equal to 1, so I can substitute that into these 2 equations. Therefore, my 2 equations are 4 equals a minus b, and then I have a 1 that goes in for c, plus 1. My next equation, 0, equals a plus b, and for c, I'm going to plug in a 1. Let's simplify each equation by subtracting 1 on both sides. When I do that, I'm going to get 3 equals a minus b. Here, when I subtract 1, I'm going to get a negative 1 equals a plus b. If you recall from systems equations, I have these stacked on top of each other with like terms on top of each other. And since I have coefficients which are opposite, I can add these 2 equations together. That gives me 3 minus 1 is 2 equals a plus a is 2a. And the b's will cancel out. Now I can just solve for this small equation. when I divide by 2 on both sides, I'm going to get A equal to 1. Now I can substitute this value into one of these two equations, and when I do, I'm going to get here, A is 1, 1 plus 1 is 2, subtract 2 on both sides, I get B equal to a negative 2. Now I substitute my A, B, and C value back into the general function. So here y equals A is 1, so therefore that's 1x squared, which is just x squared. B is a negative 2, so I substitute in minus 2x. And C, I know, is 1. So the quadratic function that represents this set of ordered pairs is y equals x squared minus 2x plus 1. Let's follow the same format for this example. Again, we have y equals a x squared plus bx plus c. We're given 3 ordered pairs for x and y. So I'm just going to substitute in, creating 3 equations. Here, y is a negative 1, substituting in, I get a negative 1 equals, x is a negative 4. A negative 4 times a negative 4 is 16, times a is 16a. X is still a negative 4. Substituting in, I get a negative 4 times b, a negative 4b. And I have c. Our next equation, y is a negative 5. Substituting in, x is a negative 3 squared, which is negative 3 times a negative 3, which is 9, times a, which is 9a. Substituting negative 3 in for x, I get a negative 3 times b, which is a negative 3b plus c. Our next ordered pair, y is a negative 7, substituting in, negative 7 equals, x is a negative 2 squared, negative 2 times a negative 2 is 4, times a, which is 4a. Negative 2 in for x gives me a negative 2 times b minus 2b plus c. Now, I need to solve for a, b, and c. And what I need to do is to take 2 equations, and I'll do that here. I'm going to take the first two, a negative 1 equals 16a minus 4b plus c, and stack that on top of a negative 5 equals 9a minus 3b plus c. What I need to do is get one of my coefficients to be opposites, and I think the easiest thing to do is to multiply the bottom fraction or top fraction by a negative 1. I'm going to choose the bottom one. And when I do that, multiply by a negative 1, that'll turn that into a negative c. And then I can add these two together, and these c's will drop out. That'll give me a negative 1 equal to 16a minus 4b plus c. The bottom equation will give me, when I distribute by a negative 1, 5, negative 9a plus 3b minus c. When I add these together, that's going to give me a 4 equals 16a minus 9a is 7a minus b, and the c's eliminate. So now I have an equation with 2 unknowns. That procedure I did with the first 2 equations. I want to do the same procedure with the next 2 equations and eliminate c again. So I'm going to multiply by a negative 1 on the bottom equation. That will give me on the top a negative 5 equals 9a minus 3b plus c. Multiplying this equation by a negative 1 gives me 7 equals a negative 4a plus 2b minus c. Then I add them, and my c's will eliminate. That gives me 2 equals 5a minus b. And from my previous equation, I have 4 equals 7a minus b. And 2 equals 5a minus b. Multiplying by a negative 1 on the bottom, that will give me 4 equals 7a minus b. And on the bottom, when I multiply that by a negative 1, that gives me a negative 2 equals a negative 5a plus b. And when I simplify, that gives me 2. The b's will cancel, and 7a minus 5a gives me 2a. Then I know that a is equal to 1. I can take a equal to 1 and substitute it in to one of these two equations. If I substitute in here, 7 times 1 is 7. Subtract, I get a negative 3 equals a negative b, or b equals 3. So now I know that b equals 3, a is equal to 1. Now that I have a and b, I can substitute it into one of the originals. Since I have one of them or two of them on this screen, I'm going to substitute it into the top one. When I do that, I'm going to get negative 5 equals a, which is 1, times 9 is 9, minus 3 times b, which is 3 times 3, which is 9, plus c. Therefore, when I simplify, c equals a negative 5. Now I know that a equals 1, b equals 3, and c equals a negative 5. My general function is y equals a x squared plus b x plus c. Therefore, when I substitute, y equals a, which is 1, x squared, b, which is 3, x, and c is a negative 5. And that function represents that set of ordered pairs.